what we did, remember we talked about method of proofs. We introduced the first one. The first one was a direct method. That's the one that you did on the test. The direct method is just a statement would be given to you. You want to prove it. So you directly, you assume the given information is true for one element, and just we take it to get, to the other one. Like the problem that you did have on the last problem on the test. Now, the next step as 4.1 is sometimes you may have to disprove a given theorem or disprove a result in mathematics. If you want to disprove a result in mathematics, one example would be enough. You cannot prove any statement or any theorem by just giving examples. But if you want to disprove it, we need an example. That example is going to be called a counterexample. So this method, disproving a theorem by using counterexample, we call it, okay? So let's see if I can get this one better. Just working with this camera somewhere else at the university, then I bring it home. Okay, now we got it. Yes, what's the question?
The question I have is, so we're still continuing chapter 4.1, and then the homework that's going to be collected on October 6th is going to do 2.3, 3.1, 3.2, and so on.
Yes, that's it depends how far we are going to go. So whatever section we covered, you should do your homework.
And then I know we skipped 3.3. Do you still want us to do that homework?
No, not 3.3.
Okay.
No. The section that I covered, anything I covered, then you just do your assignment.
Gotcha.
Okay, let's see how far we can go, then we give you an idea. But just do your problems, okay? Now, so we are still in section 4.1. The 4.1 is a very dense section. We just did the part 1. So this is going to be kind of part 2 of that section, okay? I told you, your book just repeat this idea over and over in various sections, but we're going to make it brief. So just follow the sections that we covered. That 3.3, sometimes we teach it, sometimes we won't. So that's why no, we are not going to have it. Okay, so we are still in 4.1, let's say part 2. What's part 2? Very important idea, okay? We are going to disprove this time. Okay, we are going to disprove this time by presenting a counterexample. Okay, we call it disproof by counterexample. Sometimes it's mathematics. In mathematics, it's much more difficult to disprove something rather than to prove it. This is going to be now. What's going to be the idea? Remember, we talk about the expression, the theorem that you are going to prove is this. You see, suppose you want to disprove a statement like. So if you want to disprove a statement of a theorem, you know that the statement would be a conditional. Okay, the statement is going to be a conditional implication. So this is the statement that you want to improve for all x. If px, then you get a qx, like the one that you did for the direct proof. So suppose you want to disprove this one. So in order to disprove it, so what you're going to do is you are going to say that this is not true. If this is not going to be true, so the negation must be true. Okay, so in order to disprove this statement, so V or one should prove what? One should show that or prove that. One should show that its negation is a negation. Okay, is a negation is going to be, so what's going to be the negation? Remember when we negate this one, so let's say the negation, it's negation, which is the negation for all x. If px, then qx, Okay, so we should prove that this is true. So if you don't believe that the theorem is true, so the negation must be true. Now, what is this negation? Remember? That what is the negation of for all x? If px, then qx. Anyone to try? Remember? Give us the negation of this statement.
Is it there is some x, px,
Yes, there is some x, then
p of x, and not q of x?
excellent, yes, p of x, but not q of x. That's it. Yes. So what we should prove this is it. We should show that there is an x, okay, there is an x, such that for that x, p of x is true, but q of x is false. You see, that's going to be the idea. So one should, since there is some or one, you have to find it. Okay, so one should find a value of x, a specific one. Should find a value of x for which value of x for which what? For which p of x is true. Okay, p of x is true, but or and q of x is false. Q of x is false. So you are interested in that a specific number, you see. You should find a value of x that satisfies this condition. For that value of x, p of x must be true, but q of x must be false. If you can find it, this example is going to be called a counterexample. Okay, such a value of x. So such an x is going to be called a counterexample. A counterexample. You see, that's the idea. So you have to give us a specific example. A specific example to show that, your statement, you already got the statement here. So your example would satisfy the P of X, but it won't satisfy the Q of X. This example is going to be called a counterexample. Any question? So to reject something in mathematics, one example is correct, is enough. But you cannot prove anything in mathematics by using examples. When you want to prove, to show that this is true, so you have to give us a true statement, okay, a proof. Any question? Now, to find these counterexamples are not going to be easy. There are some very famous counterexamples in any discipline in mathematics, and most of you already done linear algebra. We have a couple of very famous ones in linear algebra. And there is one that it's still open in linear algebra, but it's quite interesting to know that all these famous theorems, we call them conjecture, something that they propose to be true, but they couldn't prove it. Those conjectures run for many years. It was a computer science engineer. He just gave us counterexample. You better know his name. His name is Inflow. Inflow. And I think he's retired now. We used to be in University of Chicago, or that's it, yeah. So you just search his name, you will see. He has created those counterexample, which is not easy. His counterexample, one of his counterexamples was around quite a long time, even when I was a PhD student. So from time to time, because there were nobody else to read it and confirm it, that this is a counterexample, see, at that time. And there was no internet. So when the people travel, from one place to the other place, in the department that I did my research, University of Newcastle, we were one of the best, and the chair of the department was he was the chair of the London Mathematical Society. So anybody wants to do, especially in America, if they have a similar research, they usually visit that department. So when they came there, we asked, how about the inflow example? They say, oh, somebody else is reading it. Because this example is something like 105 pages. And there is something, we call it invariant subspace problem. If you have done linear algebra, that would be a familiar problem, but eventually, they confirm it that the inflow example is correct. So searching his name, you will see it. But later on, there was some other guys in America, like the other guy, his name is Thomas. Thomas, he used to be in CSU Bakersfield. He just simplified those examples and just give something in 2 pages. So they're quite interesting. If you go to the library, you will see some books, just counterexample in mathematics. So that's, that's going to be something quite interesting and sometimes difficult. Okay, so just give you an idea. Now your job is we give you something 3 or 4 a statement. You are going to reject it by a counterexample. Since this is important, we even repeat this one on the final exam. Okay, so let's see. They are not going to be difficult, but the way you write it down, you got to be careful. You see a value of x such that the p of x is true, but q is false. So that's it. We would like you to disprove each of these. This is the only job that we're going to do. Disprove each statement. Disprove each statement by finding a counterexample. By finding a counterexample. Since you want to disprove it, so 1 counterexample would be enough. So the first one. The first one is this statement that every prime number is odd. You know that the prime number is divisible by the number itself and 1. And start with the 2. 1 is not a prime number. 2, 3, 5, 7, you know that 11, 13, 23, etc. They are going to be prime numbers. So this statement is that every prime number is odd. So we want to reject it. So what you are going to do, you are going to give us a prime number. You are going to give us a prime number, okay, a prime number that is not going to be odd. What is that prime number?
2.
2. So this is how you are going to explain it. You see the solution. You are going to tell us that the p equal to 2. P equal to 2 is a prime number. Okay, is a prime number, but or and, but it is not, okay, it is not odd. So this is the way you reject it, exactly the way we did it here. You see, there is a value of x such that the px is true, but qx is false. So this is how you express your, don't just say 2. Just repeat this expression so that we know that you know how you are expected to prove. Any question? So it's done. That's going to be your counterexample. Give you another one. You have some nice one in your practice one, and then in your book and the exams. Okay, that's it. The next one. All multiples. All multiples. All multiples of 3 are odd. You know that multiple 3 means 3. 3 times 2, which is 6. 3 times 3, 9. Okay, 9, 12, 15, etc. These are multiple of 3. When a number is a multiple of 3, of course, that number is divisible by 3. So you want to reject this one. All multiples of 3 are odd. Any suggestion?
6.
6. Yes, 6 is a multiple of 3, but 6 is even, or some other numbers, okay? So the solution is going to be, for example, 6. 6 is divisible by 3 is a multiple. Okay, this is going to be a multiple is a multiple of 3, okay, multiple of 3, and is even, is not odd. Okay, you know that there are some other examples too. 12, or that's going to be the other one. Is divisible by 3, but is not odd. Any question? So this is how we're going to reject it. Give you another one. Again, we are going to stay with the course of the book, if you like, menu of the book. And we suggested that we're just working with the numbers. So we're just working out some problems that you'll be able to give us counterexample regarding the numbers. Okay, this next one is interesting. For every, okay, for every real numbers, every real numbers, A and B, two real numbers, and whenever if A squared is equal to the B squared, okay, always that would imply that A is equal to B. Some people think that this is true. It's not in general. Okay, it's not in general that if A squared equal to the B squared, then A would be equal to B. So we want to reject it. You should give us two numbers. Any suggestion? Two numbers which have the same squares, but they are different.
-2
And
and 2.
yes,
Why
that's
shouldn't
it.
are those different though?
Yeah, no, that's different. A is -2 and B equal to 2. Because you know that you should have the equality, then non-equality, if you like. Yes, you are right. So the solution is going to be, that's it, if A is equal to 2 and B is equal to -2 is going to be the case, then the first part would satisfy. So we have the A squared equal to the B squared, A squared equal to the B squared, which is equal to 4, but we know that A is not equal to 2. So we reject it right away. Any question? You know that you have to take the square root of both sides. These two must have the same signs, if you like. Both of them must be positive to be able to get this one. If one of them is going to be positive, the other one is a negative, you won't get it. So because you need absolute value when you take the square. If A squared equal to the B squared, then absolute value of A is equal to the absolute value of B, not A equal to B. Okay, so this is how we're going to reject it. Any question? The more interesting one is when we work with the rational and irrational. We're going to see more of this rational and irrational in future, but this is one of them. The sum, okay, the sum of two irrational numbers. Two irrational numbers. And the claim is that is irrational. Irrational number for the time being, like like the radical 2, radical 3, pi, e. These are going to be irrational numbers that we're going to prove them later, but you can use them. Okay, so the claim is the sum of two irrational numbers is irrational. So we want to reject it. You know that the sum of two rational numbers, two fractions, 1/2 plus 1/3, of course, the result is going to be a fraction, rational number. But this claim that the sum of two irrational is irrational. So you have to give us two irrational numbers such that when you multiply, when you add them together, the result would be a rational number. Any suggestion?
Can you do 2/3 and 1/3?
No, 2/3 and 1/3, they are rational. You need two irrational numbers.
What about pi and 1 minus pi?
Yes, that's good. Yes. Pi and 1 minus pi is good. Yes. Even pi and negative pi would be good. Yes. Pi and yeah, 1 minus pi. Yeah, okay. We go for it. And this is the better one is going to be, yeah, let's go. pi and 1 minus pi. The best one was pi and negative pi. But 1 minus pi is also. The 1 minus pi, they may say, you know, you have to prove that 1 minus pi is irrational number too. Okay, but we accept it. Pi and 1 minus pi are irrational. Okay, are irrational. But if you add them together, it's going to be pi plus 1 minus pi. Okay, so the pi and the negative pi would cancel out. So that give you 1. 1 is a rational number. Is rational. So you reject it. Radical 2 and negative radical 2. That's easiest one. Radical 2 is irrational number, okay? Radical 2 and, you see, radical 2 and negative radical 2 are irrational. But if you add them together, you see radical 2 plus negative radical 2. That would be 0, is rational. Okay, you have a number of these expressions regarding the rational and irrational, so just get to know them, and we're going to have more. Okay, so this is going to be number 4. Any question? Again, if you want to stay with this irrational, you have these. So let's get practice because we have it in your assignment. The other one is for the product. The product. Okay, the product of 2 irrational numbers. Of 2 irrational numbers. 2 irrational numbers. The claim is that is irrational. Is irrational. So you need 2 irrational numbers whose product is irrational. Any suggestion for this one?
It's just any irrational number times itself, like squared, like root 2, root 2.
Yeah. You have to give us, 1 because precisely, yes, that's it. So the claim is, yes, radical 2 is irrational. Okay, is irrational, but radical 2 times radical 2, there's going to be radical 4. 2 is rational. Is going to be rational. Okay, so this is the way you're going to reject it, reject this fact. Okay, any question? So that is proving by counterexample. So you know it from now on that in this course, if you want to reject something for us, you have to give us a counterexample. Okay, but remember, if you want to prove that a statement is true, never use examples. You may use some examples to get an idea if you want to prove it, just an idea. But actually, if you want to prove it, you have to prove it. You have to use some theorems, definitions, logical identities to be able to get rid of it. Okay, so this is the way we do it when we do research. The way we investigate. Sometimes we arrive at something. We try to prove it, but we may get some ideas, some hints that it may not be true. So you try to make a counterexample, okay? So that's going to be, sometimes you may have to spend quite a lot to find out that your result is not going to be a positive result, okay? Any question? So that's a proof by counterexample. If you get time, just check the name of the inflow, especially if you are most of you computer science students. So to get his, to know him that most of the good, although he's not a pure mathematician, but so far he just solved 2 famous problem from pure mathematics, and he just used pure proof, not like nothing to do with the computer science. The method that he is going to use is called strong inductions, and that would be our topics in chapter 5. When we get to that one, I just give you some hint, the work, the way he did it. Okay, so that is 4.1. Any question? So what we did so far, we did the direct proof, something would be given, we try to prove it directly. If we cannot prove it, we provide a counterexample. Okay, so that's done. Now what's going to be next? You see, in mathematics, we have some more interesting method of proofs. These method of proofs are going to be called indirect one. Okay, so the other one was a direct one. You start with P of X, you end up with QX. These are going to be called indirect proofs. In the case of the indirect proofs, we are going to use some property. Let's talk about it. We have the two famous methods of the indirect proofs. One of them is called proofs by contrapositive. Remember, contrapositive argument that we did have. And the most interesting or important one is going to be method of contradiction, which is the most popular one in mathematics, okay? And then we have one more method that's a method of mathematical induction that would need all topics on the chapter 5. Okay, so we go to the, this would be briefly in 4.7, I think, in your book. In between, they give you lots of argument. You can read it for yourself, but you are not going to get anything other than the one that we talk about it. So we are going to talk about what is indirect proof. Okay, indirect proofs. You get, just check the section that I posted on the assignment, and you will see it. And it's going to be 6 and 7. I think on 6 they talk about just rational numbers, the property of the rational numbers. That we assume that we know it, and we go with this one. But that's it. What is going to be indirect proof? 1 hour only. Indirect proofs, we have two types of proofs. The first one is called proof by contrapositive. Quite interesting one. Proof by contraposition or just contrapositive? Contrapositive. They are going to tell you, they say proof by contrapositive or contraposition. Now let's recall, remember the contrapositive? The contrapositive test is that if P then Q is what is equivalent with not Q, not P. So let's recall this one first. Recall that by contrapositive law, that we did it before and we used it quite a lot. If P then Q is going to be equivalent with what? Not Q implies not P. So what we're going to do in this method? So in this method, and a statement would be given to you, you want to prove it. You want to prove if P then Q. Sometimes it would be easier to prove the other side. You see, so instead of proving if P then Q, we are going to prove that the negation of the Q would imply the negation of the P. And the theorem may be much, much easier to prove, okay? So what we are going to do in this method is therefore, okay, therefore in order to prove, okay, in order to prove a theorem that has of the form, okay, that has the form, you know that each theorem would have this form of, let's say, if P then Q. So we must prove, or one can prove, or try to prove, one can prove equivalently. Okay, equivalently that not Q implies not P. Okay, this method is going to be called method of contrapositive or indirect proof. So the statement would be given to you. Your job is carefully change it to this format first. Okay, that's very important part. So this would be given to you. There are some quantifiers that you have to nicely negate it. So you change it into this format, and then you are going to prove this one directly, as we did it for the direct proof. Okay. So this method is going to be called method of contrapositive. Any question? Now let's try to see how we're going to deal with this. Again, the instruction would be given to you. So we're going to give you that proof. Okay, proof by contrapositive. Proof by contrapositive. That's how we're going to do it. There will be some famous one. Again, these are part of your job. We may ask you directly to prove this on the test. Okay, these examples that we give with this method, so you must know them. Okay, so the first one is, you want to prove this one. If x is an integer, if x is an integer and x squared is even. Okay, so this means if the square of a number is even, the claim is then x must be even too. X is also even. Okay, so this means if the square of an integer is even, then you want to prove that the integer is also even. Okay, it's very famous result. If we ask you directly to prove it, you must know it. Otherwise, if it's going to be in some other problem and you want to use it as a part of the problem, you are free to use it, okay? Because I'm going to use it later on to prove one very famous theorem. Okay, now how are we going to prove it? They ask for the contrapositive. So you have to write the contrapositive as this statement first. So you are going to check that this is it. You check this one to be P. P is the fact that the Q squared is going to be even. Okay, and this is going to be what? This is going to be Q. So you are going to tell us what you are going to prove. You have to write the contrapositive of this one first, okay? So the proof is going to be, okay, that's it. So the proof. You start with this fact that, you just tell us what you want to prove. So one or we should prove that. That's it. Now, the contrapositive of this statement. So what's going to be the contrapositive of this statement? Any suggestion?
If x is odd or if x is not even, then x squared is not even.
That's it. Yes, excellent. So this is what we have to prove, that if x is not even, which is the same as to be odd, okay, then x squared is not even. Not even, so it's going to be odd. Okay, so you have to give us this statement first to know what you want to prove. Now we are going to do it. So this means if x is odd, you know the definition of the odd numbers. So we say, okay, I suppose now that, suppose x is odd. So you know what does it mean? X is odd, so means there is a k such that x is equal to 2k plus 1. That's the definition of the odd number. Square it. So what is going to be x squared? So the x squared would be 2k plus 1. 2k plus 1, all square it. You can FOIL it for the square of the binomial. So it's going to be a square of the first one, which is 4k squared. Twice of the first times second, 2 times 2, 4k plus 1. You want to prove this odd, you know that. You have to change it to the form of the 2k plus 1. So we better pull out a 2 here. So that's going to be 2, and this is going to be 2k squared plus 2k plus 1. Now we can call this one k1 because it's going to be an integer. So the result is going to be 2k1 plus 1. Okay, so which is x squared. That's it. You know that what you proved is you show that there is a k1 such that x squared is equal to the 2k1 plus 1. I just repeat it. And so x squared is going to be odd. And that's exactly what you want to prove. Okay, so you start with the fact that the x is odd, then you prove that x squared is going to be odd. Now you are going to repeat this expression. You are not done. You say, oh, by contrapositive. By contrapositive or contrapositions, contrapositive law. Now your statement what you want to prove. If x squared is going to be even, then x is even, and you're done. So that's the way you prove these type of ideas. So you have to change the given expression to its contrapositive, and then you prove the contrapositive. When you prove it, you just go back, say, oh, by contrapositive. So what I did is this one, that if x squared is going to be even, then x is also even. Any question? So it's going to be true for odd. You can use it. So I write it down. I don't prove it, but you can, we may ask you to prove that one on the test, and you can use it anytime you like. Okay, any question? So in future, if you have the case that x squared is even, automatically you can conclude that x is even. Or if it's going to be odd, let me just write the odd one so that make sure that you know it and you prove it for yourself. So that was the first example. The second example is going to be this one, that if x squared is odd, then x is also odd. You know that, write the contrapositive version and just prove it as I did it. It's in your next review, and you will see it. Okay, any question? So that's going to be what? There are a couple of them which is very clear, okay, when you change it to the contrapositive. But sometimes some people on the test try to do more and more. You don't need it. You have this number. It's very popular. It's in 2 places in your book. And we may give you a version of this one. So don't be surprised. You see, this is it. You want to prove? You want to prove this, that if the sum of 2 numbers, okay, x plus y, is bigger than something, is bigger than 5. Okay, if the sum of x plus y is bigger than 5, then the conclusion is going to be, for example, x is going to be greater than 2, or y is going to be greater than 3. They break it into different numbers. In this case, I give you 5, 2, and 3. You can have it for various numbers. And all of them are going to be, okay, are going to be the same thing. Okay, are you ready? They ask for the contrapositive. So what's a contrapositive as this statement? Remember, you have to start with the contrapositive one. So you have to start with the fact that you say, oh, one should prove, or I should prove. One should prove that, okay, what's contrapositive as this statement? Who wants to try?
If x is less than or equal to 2 and
Yes.
y is less than or equal to 3, then x plus y is less than or equal to 5.
Excellent. Yes, that's exactly what we should prove. So the contrapositive as or would be and, very good. So if, I should prove that if x is less than equal to 2 and y is less than equal to 3, then x plus y is less than equal to 5. You see, this is 50% of the proof, just to find out what we want to prove. So quickly pick 2 numbers. Okay, this is how we're going to do it. So, oh, okay. Suppose I be given the fact that x is less than equal to 2 and y is less than equal to 3. You see, so suppose these are going to be now are given to me. So then you see, then you want to connect them together. The connection is addition. So we are going to use some facts from algebra or arithmetic, algebra. You know that when x is less than or equal to 2 and y is less than or equal to 3, we can add the terms of the inequality. So this means x plus y, you see, is going to be less than or equal to the 2 plus 3. That's a fact. That's a basic property of the inequalities. So this basically means what? Means x plus y is less than or equal to 5, and then you're done. You see, not a big deal. On the test, I gave several times a similar one. Some people, in order to get to these 5, you see, they just try to give some examples. They start with the fact that x equal to 2, y equal to 3. They say addition, we get a 5. Then they pick some other numbers. No. Remember, it's a proof. For the proof, no examples. It's fine. It's fine because we find out what we want to prove. That's why we change it. And then we're just using the easy facts of the inequality. That's part of the deal, that if you have inequality, you can add the terms, the sides, and you get the same in the same direction. So we're just using the property of inequality and we prove, and this is done. Okay, any question? But you have to get back to what you want to prove. You say, oh, so by contrapositive, you're not done. You have to end up with this expression. So by contrapositive or contrapositions law, you just repeat your statement. So it's going to be if x plus y happen to be greater than 5 strictly, then yes, then one of them must be bigger than 2, or the other one must be greater than 3, and you're done. Okay, any question? So don't be surprised. This is easy proof, but it's important to organize it. You see, if you don't organize it, if you don't start with this idea of that you are proving the contrapositive equivalent, your proof is not sounded, if you like. So don't be surprised. Any question? So this is one. We have another class. So look at this one. Some form of the numbers would be given to you, and they ask for the odd, and even like one of the mild one that you did have in that in your test. I think that was one of them. So let's see again to make sure you know how to handle these type of problems. That's it. You have you be given a number. Suppose x is an integer. X is an integer. Okay, then we want to prove this one. Prove that. Remember, you did have something like 5n plus, I think, 1 that you prove it was odd number. In this case, they ask you to prove that if x squared plus x plus 1 is even, then x must be odd. That's interesting, the way we just using this method to prove it. Okay, x is any integer. We want to prove that if x squared plus x plus 1 is even, then x is odd. And we want to use the contrapositive property or the contrapositive method. Okay, are you ready? So what's the contrapositive of this statement? The one that you want to prove, you see, if x squared plus x plus 1 is even, you want to prove that x is odd. So what's the contrapositive equivalent? Anyone to try?
If x is even, then x squared plus x plus 1 is odd.
That's it. Yes, excellent. Yeah. If so, again, you say that the one should prove. One should prove that. That's it. If x is even, then x squared plus x plus 1 is going to be odd. Remember, it's a not p, not q, not b. Okay, so that's a very important part of the problem. Now we start, we pick one. Any question? So we pick one here. Okay, suppose you give me that. Okay, suppose what? Suppose x is even. X is even. Go with the definition even right away. Definition of even, it's going to be multiple of 2. So this means there is a case such that x is equal to the 2k. Okay, but we want x squared plus x plus 1. So let's take that on. So we want x squared plus x plus 1. So we substitute. So that gives us a 2k squared. Okay, plus the 2k plus 1. You work on this one to get an odd number. So that gives us a 4k squared, and that's going to be the 2k and the 1. Okay, as usual, you want a form of 2k plus 1, so you better pull out the 2 here. So we pull out the 2, so that gives us a 2k squared plus k. Okay, plus 1. Okay, 2k squared plus k plus 1. And what else? So we're going to call this one something like k1. Okay, k1. So the result would be what? Would be 2k1 plus 1. So we have the x squared plus x plus 1. Okay, of this form. So this basically means what? This means this is it. I just repeat it. So what I did, I find the k1. You don't have to. I find a k1 such that this is going to be 2k1 plus 1. And so x squared plus x plus 1 is what is odd. Okay, and this is what we were looking for. But you have to end up with by contrapositive. Okay, that's it, by contrapositive. So by contrapositive, you repeat the expression that you want to prove. If x squared plus x plus 1, okay, x squared plus 1 is going to be what? Is even. Okay, if it's going to be even, then x is odd. And then we're done. Okay, so write it down nicely. You see, it's a proof. It's a proof, and just step by step must be logically correct. And you know it, why not? So we put them together nicely to get these results. Okay, any question? So that is the method of contrapositive, if you like. Okay, it's going to be method of contrapositive, and the other one was a method of counterexample that we did. Okay, so we are going to go to the last method, which is quite interesting method. Let me just, and that method is going to be method of contradiction. Yeah, it's something here. You can find it. And okay. Give you, no, just want to give you a counterexample that I make myself. Just show you now the way we are going to do the no, I can't find it now. Yeah, I show you later that when I was doing my research, we were working on a problem for a couple of years. Then we built up a theorem, but everything was based on based on a paper that we read that paper. Let me show you. But my advisor told me that, oh, okay, so now you want to publish the result, so you better go and prove that result that you used. But we tried to prove the result. I can't do it. It was so obvious. So he said, it's very, it's very easy. Go and prove it. So I couldn't prove it. And I didn't want to go to, to see him because he said it's so easy. But then I just, we have some doubt about it. Maybe it's not true. I take him to him, okay, and he said, oh, that's easy. I can prove it for you. He tried, but he find out that it was not easy. So there was something wrong with it. So what we did, we made a counterexample. And we lost that theorem, but eventually, okay, we proved something. So this is the way, we do the business of these ideas. I'm going to share this one with you. Just have a look to see what type of research you may do in future for yourself. This is the paper that I published in a Canadian Bulletin of Canadian Mathematical Society, years ago. Can you see it?
Yeah.
This is it. It's kind of, a little bit of linear algebra and some others. And this is Canadian, Bulletin of Canadian Mathematics, 1993, of course. That's MIT and function analysis. And this is the name of my friend. He passed away. He was a great mathematician, graduate of Indiana University. So this is just show, the kind of counterexample. You see, this was something, you may not understand the things that we have over here. It was a proof, they call it the stronghold. It was a theorem that we tried to prove, but it was not possible. So eventually we make this, we make this counterexample, if you like. This is the example that we eventually, that's the example. You see this one. And the guy who just had the book, his name is Gamelin. He was in CSU Riverside, UC Riverside. He was a great mathematician. In his book, there was, you see, this example showed that the normality of P cannot be omitted. So we add this condition. You see, when you reject, you cannot do something in mathematics, you add an extra condition. We add an extra condition to his things, and we proved it, and then we provide a counterexample. That's a counterexample. We prove a counterexample to show that, he's, we just reject that idea. So this is the way we do mathematics. At the end of the day, you may not be able to prove the theorem, but if you have a very nice counterexample, then you can go back. And this counterexample is not a difficult one. It's based on some, the way we put it together, of course, it takes time, but it's a kind of, we're just using a function in calculus, e to the negative x squared. But anyway, just to show you, these are going to be used all over the places. It doesn't matter at what level, or are you a pure mathematician or not. Okay, so to just give some idea for the next interesting method. So that's a method of disproof, okay? So we know that this statement was true, but we cannot prove it. We just use the disproof to prove it. Now, we have a last method, which is the most important one. This last method is called method of contradiction. A method of contradiction is very similar to the contrapositive. So the method of you see, in the contrapositive, instead of proving if P then Q, we prove not Q implies not P. In the method of contradiction, again, we assume that the statement is false. When we say a statement is false, this means this not Q is true. So we stay with the not Q. It's very similar to the contrapositive, because that's why some people will be confused. We stay with the not Q, but we don't arrive at the not P. We show that if not Q is going to be true, you arrive at the contradiction. Contradiction would be something contrary to the everyday life, contrary to some theorems in mathematics. That is the method of a contradiction. But in order to get it, we are going to use some property of the rational numbers for the examples that we have. So I briefly review this property. It's one section of your book. but we don't need much of that one, just the following. So this would be in 4.8. I briefly give you what we need for the rational numbers first, because we need them in order to be, our examples are going to be all related on the rational numbers. Okay, so review, we just gave a pause if you like. We build up the rational numbers. Everything I write here or we talk about it, you can use it. You don't need anything else. So we are going to review, okay, review rational numbers. Seriously, okay, this is what we need to know for the, because we have 4 important problems and all of them would be given to you on your next quiz, and the test would be related to this idea. Okay, let's see what's going to be rational number. Remember, a ratio of 2 integers is called a rational number. So let's make it official. If A and B, okay, if A and B are integers, A and B are going to be integers with B not equal to the 0. Okay, then A over B. Okay, the denominator is kind of 0, you know that. It's going to be called, okay, is called a rational number. A rational number. So that's the definition of a rational number. Okay, example of rational numbers like what? 5 is a rational number. You know that 5 is 5 over 1. -2 is a rational number. 0 is a rational number. 1 is a rational number. Okay, then you have the 1/2 is a rational number. Okay, then you can have a 3/2 is a rational number. 1/5 is a rational number, etc. Okay, so these are going to be what our examples are going to be. Examples of rational numbers. Of rational numbers. So from now on the proof of those problems that I talk about it, anytime you want to introduce a rational number, you say A over B, but quickly you have to write that the B is not equal to this 0. Okay, now what can we do with the rational numbers? Fundamental operations. What is that? Addition, subtraction, multiplication, and division. We say that this set of the rational numbers are closed and their fundamental operations. What does it mean? This means the sum of 2 rational numbers is a rational number. The difference is a rational number. The product is a rational number. And the division could be a rational number. Okay? So freely you can use all of them. And you are going to use all. Okay? So remind you addition, subtraction. Okay, it's addition, subtraction, multiplication, and division or dividing. Division of, in your book, they talk about all of them, you know, one by one, but this is all we need. Of rational numbers are defined, okay, are defined as usual. What does it mean as usual? This means if you have 2 fractions, you see A over B, if you want to add it or subtract it to C over D. Okay, you know that we find the common denominator. So the common denominator would be what? Would be BD. And on the top would be what? Would be AD plus or minus, okay, DC. And since B and D are not equal to the 0, you know that this denominator is not also equal to the 0. You see that's going to be the 1. B is not equal to the 0. And the D is not equal to the 0. As you can see, if you add or subtract, the result is again is a rational number. because the only condition that you need is just the bottom is going to be a non-zero number. Okay, so this is a rational number. Is a rational number. So if we need to use this fact in our theorems, we are going to use it without any proof that the sum of two rational numbers is a rational number. There you are, the difference is rational. Okay, any question? Then the multiplication, you know that easy to multiply. If you have A over B, you can multiply by C over D. Fractions. You multiply the top together and the bottom together. Again, this denominator is never zero. So this would be what? Again, BT is not equal to the zero. So this result is a rational number. A rational number. So the product of two rational numbers is a rational number. Okay, any question? You know the division is a kind of multiplication. A over B, this is C over D. You know that we write the first one multiplied by the reciprocal, so that's going to be DC. So the top again would be AD, and this is going to be BC. Okay, that's one. Again, this is going to be what? This is going to be, of course, you know, when you divide C is never zero because you divide it. So this is also is a rational number. Usually talk about addition and multiplication because subtraction, you know that subtraction is the opposite of the addition and the division is the inverse of the multiplication. So we just need those two. Okay, so as you can see, I show you and I proved it that therefore, what I was talking about, therefore, rational numbers. Okay, rational numbers are closed, that's the expression. Closed under usual operation. Usual operations. Okay, close, I just write one of them. See, the close means this is it. If you like, the sum or the product, if you like, or the product of two. The rest are going to be, you know, the subtraction and division follows from these two. Okay, the sum or the product of two rational numbers. Okay, is rational. So we need this, and you can freely use it anytime you like. Any question? So that's a total one section, you know, in your book that they talk about these arguments, but you know, we are going to use it freely. Okay, for the that's a fundamental to the example that we're going to have for the contradiction one. Okay, any question? Now let's see if we can give you at least the idea of the that last method. Okay, very important method, and you quite a lot. Everything in this section you have to, okay, this method of contradiction. You read it and we're going to do it for you. That's it. What is proof by, this time proof by contradiction. Contradiction. The most popular one in mathematics is this one. Okay, we already done it. This is again indirect proof. For the indirect proof, we have two cases. The case with just using contrapositive, and the other case is contradiction. Okay, let's see what you want to prove. You see, as we talk about it, you want to prove that if P then Q. Okay, if P then Q. For the contrapositive, it was equivalent to the fact that the not Q implies not P. But over here, what we are going to do is we are going to start with the not Q, but we try to arrive at the contrary Okay, a contradiction, something contrary to the fact. Let's just build up the argument again. You see, let's check it again in this method. Okay, method of contradiction, method. To prove this statement, to prove, as usual, the statement that prove the statement that that if, as usual, if P, then Q. Okay, so what we're going to do, we assume it's false. We assume that the statement we assume that the statement is false. The statement is false. Okay, what does it mean? A statement is false means, you know, the negation is going to be true again. That's it. That is the negation. The negation of the statement. Of the statement. You know that the negation of the statement of P then Q is what? As usual, we did it before. It's going to be P and not Q. We assume this is true. Okay. We assume this is true, you know, you just assume that, oh, there is a X slash that PX is true, but Q is not. Okay, or in general, we say that, oh, we want to prove that if P then Q, we say suppose not. Suppose not means suppose Q is not true. Okay, so we assume this is true, and then we apply some definition as usual. We apply definitions, depends on the nature of the problem. Some logical argument. Okay, some logical argument to arrive. Okay, to arrive at a contradiction. You see, in the contrapositive, you start with the not Q, you arrive at the not P. But in this case, you start with the not Q, but you are not going to arrive at the not P. You arrive at something that is so well known that you know that you reject it. So it's going to be something contrary to the custom we say to get these numbers. Okay, so that would be the method of contradiction. Okay. Now, all other examples, the nice one, are related to the rational numbers and irrational numbers. And most of them are going to be depends on this next fact that, you know, the radical 2 is not a rational number, or radical 3, radical 5. And so since it depends on the radical 2, we prove this one first. Then I give you those problems. I prove this one. This means on the test, you can use it without any proof, unless we ask you to prove it. You know, since we're going to give you an exam on Zoom, we are not going to give you this one to prove, but the method is important, okay? So this is, you can use it anytime you like. A radical 2 is irrational. So I prove this one, then you can use, you know, radical 2, radical 3, radical 5. They are going to be irrational numbers. The proof is interesting. It's part of the history of these subjects, okay? So let's prove it, see how we're going to do it in counterexample 1. You see, I want to use the method of contradiction. So what I'm going to do is say, suppose this is false. The expression that we use, say, oh, suppose not. Suppose not. Suppose it's not true. Suppose not. Suppose not means what? Means assume the other way around. Assume that radical 2 is a rational number. You see, this must be your starting statement all the time for the contradiction. Whatever is given to you, you assume it's wrong. It's false. So it's false, the negation is true. So you assume that the radical 2 is a rational number, now you arrive at the contradiction. How are you going to arrive at the contradiction? It's a very famous problem. You know that it was done by, for those Pythagorean identity. The difficulty was, you know, that the students of Pythagoras, they were very fond of the teacher. So when they find out this difficulty with the problem, for the long time, they try to hide it. You see, the Pythagorean identity, you know that the square of the largest side is the sum of the squares of the others. So some of them that think that this is going to be 1 and 1. If this is going to be 1 and 1, the square of the 1 is 1 and 1. So this must be what? Okay, this was the question. So if it's going to be 1 squared plus 1 squared, this must be equal to the x squared. So 1 and 1 would be 2. So that would be x squared. So x squared equal to the 2. So they should have an answer, but the answer today we know that it's going to be radical 2. But for the time being, because they didn't have the irrational numbers, so they suspected that the theorem is not true in general, and they hide it for the long time. They didn't ask the question that it's going to be the case. You know that they use geometry to take care of it. If you have done it in high school, or you can search it for yourself. That they bring something very similar to what we call it irrational numbers, but they use geometry to draw the radical 2, radical 3, radical 5, and they were taking care of it. So that's the original idea of this number is not going to be a rational number. But today we have some modern definition or proof, and this is going to be the one. We assume it's a rational number, and then we are going to reject it. So what's the definition of the rational number? Remember? Therefore, there is an A and there is a B with the condition that the B is not equal to the 0 and radical 2 is equal to the A over B. That's definition of a rational number. So we try to make a counterexample. Maybe we try to make a contradiction. Now, you see, when you write fractions, we always we write it so that if the top and the bottom can be simplified. You see, we simplify it. We say reduce form. So if you have a 2/4, we divide by 2, that gives 1/2. So we assume that it's already been simplified. When it's a simplified, so A and B, they are not going to be divisible by any number. So we say that they are not going to have any common factor. And that's very important, okay? So we assume that these numbers, A and B, they have no common factor. Have no common factor. That's very crucial to arrive at the contradiction. Any question? It's not a big deal. If it is, we just change it, see? If they have the common factor, so we simplify that, give us a 1/3. Okay, so we assume that we already simplified it. Now let's say we're going to arrive at the contradiction. Let's start with this fact. Radical 2 is equal to the A over B. Let's square it. If you square both sides, that gives you 2, and that gives you A squared over B squared. I want to arrive at the contradiction, remember. Cross multiply. So that gives me A squared equal to the 2B squared. A squared is a multiple of 2, remember? Any number of the form of the 2K is an even. number. So this means a squared is even, because there is a 2 here. And remember, we proved for you that if the square of a number is even, then the number must be even too. So a is even. Any question? So I square both sides. I say radical 2 would be true, a squared over b squared, cross multiply, a squared to 2b squared, so it's a multiple of 2, so a squared is even. And we prove that if a square of a number is even, then that number must be even too, okay? So what does it mean? This means there is a k such that a is equal to the 2k. Okay, bring it here. But a squared is equal to the 2b squared. So that would be what? That would be 2k squared equal to the 2b squared. So this means 4k squared is equal to the 2b squared. Simplify it. 2 and 4. So what are going to have? You are going to get the fact that what? It's going to be 2k squared equal to the b squared. Or b squared equal to the 2k squared. So b squared is a multiple of 2. So this means b squared is even. But we talk about it. If the square of a number is even, that number must be even too. B is also even. Any question? So what we did, therefore, we arrive at the conclusion that A and B, both of them are even. And this is a contradiction. Why? Anybody wants to try?
Because it would make it rational.
Yes, not so directly. No, what's the contradiction with the assumption that we have here first? What part of this would be contrary if A and B, both of them are going to be even?
That means they'd have a common factor.
That's it, yes, excellent. If A and B are going to be even and 2 would be, and 2 is a common factor when it's even. 2 is a common factor. Common factor. This is a contradiction. Okay, so this is going to be, it is a contradiction. It is a contradiction. It's a contradiction because, you know, the line of argument was that the A and B has already been simplified. So if it's already been simplified, so they cannot be, you know, they cannot be both of them to be even. So since we arrive at the contradiction, this means, you know, the actual result is always true. Okay, so we say that by contradiction, therefore, no, radical 2 is irrational. See, this is a kind of, historically, this is the first time that, you know, there are many proofs of the fact that the radical 2 is a rational number. There's a book by an Australian mathematician. His name is Paul Newman. If you just check, I think it's Newman. I don't know whether it's Paul or not. But he just provided with something like, you know, 30, 40 proofs that the radical 2 is irrational. So search on the internet, you will see it. But this is a very nice and clean proof of using the contradiction. Okay, any question? Again, this is a fact that you can use it anytime you like. Not only this one, you can use the radical 3, radical 5, okay? These are going to, because these are very basic to the other problems that we're going to have in this section. So you can assume that you know it is a rational number. Then we bring other problems at the next lecture. That's one. We can, this is a radical 2. We are going to use this one, the contradiction, to prove that, for example, 7 plus radical 2 is if you have a rational number and irrational number, add them together, the result is irrational. Then the product and the quotient. These are the problems, and a couple of more. We have some more nice examples that we talk about it. Okay, on Wednesday, and we finish it. Any question? So read it carefully. So what we do the contradiction, then remember we have to do something, a brief version of the graph theory. It was in 1.4 that we didn't do it, because there are a couple of theorems that we can use this method to prove it. So 4.9 and 1.4 would be covered after this one. So we are going to be still in this one on Wednesday to finish it. Very interesting topics. That's it. Any question? So wait, we finish it, and then there are some nice examples in your book. I will talk about a couple of them, but you can have a look at those assignments that we have, and you have any difficulty, bring it in. We can talk about it. I know that a couple of them are very tricky. Those examples that we have. Okay, that's it. Any question? I tried, start working on your test today. I just do a couple of problems at a time so that we can be able to finish it by the end of this week to get these ideas. Okay, have a good one, and read this. They are very interesting part of your course, really, this method of proofs, and you're going to use it in future. So read it. If you have any idea or comment, you can bring it in and we can discuss it again. Have a good one, and see you on Wednesday. Bye-bye.
Thanks. See you Wednesday.
Bye-bye.